Most enterprise developers treat the @transactional annotation as an absolute safety net. You place it above a service method and expect the framework to manage database connection lifecycles and execute predictable rollbacks. At scale, that syntax is susceptible to failure. Swallowed exceptions, unproxied methods, and unmapped execution boundaries routinely bypass the annotation. Look at this system under load. A single unmapped checked exception doesn't just slow down execution. It causes transactions to silently drop, compromising your data persistence layers without ever triggering an alert. Declarative transactions function as a rigid, aspect-oriented programming proxy boundary, operating entirely through standard Java bytecode interception. This proxy relies on ThreadLocal storage networks to bind raw database connections directly to executing threads. Break that thread boundary, and you lose the transaction. Today, we are performing an autopsy on a dropped transaction by mapping the deterministic network of proxy layers, identifying specific propagation traps, and examining the application-level locks required for concurrency. Treating the Spring transactional subsystem as framework magic is the primary vector for silent data corruption in distributed enterprise architectures. Before any database connection is opened, Spring AOP must successfully wrap your target method. The container does this by dynamically generating a proxy class to intercept the execution path. Modern Spring Boot configurations utilize an engine called CGLIB to generate these proxies. CGLIB works by dynamically extending your target class and overriding its methods to weave in the TransactionInterceptor layer. Here is the abstract class layout for a report processor component. Notice the method is marked with the Java final keyword. Because Java strictly prevents subclasses from overriding final methods, this creates a fatal architectural trap. Due to this exact bytecode restriction, the CGLI proxy generation engine is blocked entirely from intercepting the invocation. The transaction interceptor is never applied. Instead, the execution routes directly to the raw target object. This removes your intended database transaction boundary. And because this is a valid Java execution path, the system throws no compilation or startup errors to warn you. Architectural intent means nothing if the underlying bytecode rules prevent the proxy interceptor from wrapping the execution threat. When proxy interception does succeed, we trigger the actual database synchronization mechanics. The first step in this pipeline occurs when the transaction interceptor queries the configured platform transaction manager. This schematic tracks the resource acquisition phase. The transaction manager fetches a raw database connection from an underlying pool, like HikariCP. The framework immediately executes a critical configuration change. It disables the auto-commit flag on that raw connection. Next, it establishes the synchronization boundary. The connection is bound directly to the active executing thread inside a specialized ThreadLocal storage entity called the TransactionSynchronizationManager. All repository queries executed within that method share this exact ThreadLocal connection reference. Once the business logic finishes, the thread hits the completion gateway. Upon success, the interceptor manually calls commit. Upon encountering an unhandled exception matching the rollback criteria, it calls rollback. Finally, the cleanup phase restores the auto-commit flag, unbinds the connection from the ThreadLocal registry, and returns it safely to the connection pool. Declarative transactions are merely a ThreadLocal routing mechanism designed to share a single raw connection across multiple sequential repository calls. This ThreadLocal routing demands precise governance. You must explicitly govern how transactional boundaries merge or split through propagation invariance. The default framework behavior is required. This instructs the incoming execution path to join an active physical transaction or initialize a new one if empty. We contrast this with requires new, which creates a strict isolation boundary. It suspends the outer transaction entirely and opens a completely independent physical connection. Look at these two parallel execution lanes. This illustrates a primary failure vector, combining requires new with improper exception handling. When the inner transaction fails, it instantly marks its independent connection as rollback only and returns control back to the parent method. Here is the developer error. The parent method catches and swallows that exception in a standard try-catch block. The parent method attempts to commit, but the shared global thread state is still flagged as rollback only by the nested process. Because the thread state contradicts the commit request, the execution engine drops the transaction entirely and throws a fatal unexpected rollback exception. The root cause of this initial exception behavior traces back to Spring's legacy EJB exception classification rules. Under the default rules, unchecked exceptions, like runtime exceptions, trigger automatic rollbacks. Checked exceptions, however, assume the application will handle them gracefully, and they trigger a commit anyway. The senior architectural fix is to explicitly override this behavior. You declare a specific rollback class within the annotation property to enforce clean rollbacks across all exception types, both checked and unchecked. Hiding exceptions from the global transaction manager breaks the synchronization matrix, turning safely handled errors into fatal connection drops. Managing the lifecycle of a single transaction is only half the architecture. We also have to manage concurrent database access within those active transactions. There are 4 classic ANSI SQL isolation levels. Upgrading to strict global levels like serializable prevents concurrency issues by locking tables completely, but doing so destroys system throughput under concurrent load. The senior alternative to upgrading global database isolation is shifting concurrency control down into surgical application-level locking models. This split-screen logic visualization demonstrates 2 primary application locking models. On the top half, we have optimistic locking, configured via the @version annotation constraint. Optimistic locking bypasses database row locks completely. It uses an internal primitive version column to atomically verify state. Thread A succeeds and increments the version. Thread B fails the check, updates 0 rows, and triggers an optimistic lock exception. This model maximizes raw database performance for low contention environments where data collisions are rare. On the bottom half, we see the strict alternative, pessimistic locking, via the pessimistic write configuration. This function issues an explicit raw blocking lock directly at the database hardware layer by emitting a SQL select for update statement. A solid wall anchors onto the specific row, forcing any concurrent thread into a blocking loop until it's released. This model is essential for preventing dangerous race conditions during high-contention, mutually exclusive operations, like processing microservice balance deductions. The @transactional annotation represents a deterministic state machine built on proxies, ThreadLocals, and specific propagation rules. To scale these systems safely, you must control the proxy bytecode. You have to ensure modifiers, like the final keyword, do not silently neutralize your interception boundaries. You must explicitly manage your propagation boundaries and exception rules to prevent global state corruption and unexpected rollbacks across nested services. This glowing blueprint illustrates the final mandate. Architects must surgically apply specific persistence locks to balance data safety with concurrent throughput. Master these synchronization networks to engineer back-end systems capable of surviving intense production loads. Thanks for tuning in. Hit subscribe and we'll see you in the next episode.